Thank you, Dirk. So Dirk already covered who I am, where I come from. Background, computer science, a bit of control. As Dirk said, I've been in academia, I've been in the software industry, and then I figured it was a logical choice to move to industry to see how the tools actually work in real life. I've been in the standardization committee for FMI in Modelica, so I'm very glad to be back, and I would like to thank the committee for the opportunity to speak today. So I will talk about what I learned and some experiences and maybe some challenges from the past 3 years, which I spent at Carrier. I will give an overview of that. I will focus mainly on integrated energy systems. That's one of the things that Carrier do. It's by far not the only one, but it's one piece that I think is very interesting. I will also give 2 case studies and dipstick a bit what it could look like, what the problems are, and maybe a bit of the mathematics behind, maybe fewer equations than we saw yesterday. And from there, extract some of the challenges that we are having with various tools and methodologies and languages, and hopefully maybe some of you can pick them up and help us. So Carrier, we've been doing air conditioning equipment for 115 years. I think Willis Carrier formed the company. We now also have partners with Fissmann, so there's a strong German branch of Carrier through Fissmann. We are roughly, say, 55,000 employees around the world. And we have verticals in essentially all areas where heating, ventilation, and air conditioning is needed. I will focus on district heating and cooling, and I will focus a bit on data centers today, but there are many other areas which Carrier is invested in. So to set the stage a bit around the building challenge that we have together. So 30% of the energy worldwide is spent on buildings, actually building operations. If you add building construction, there is 10% more, but I'm not going to deal with that. So let's say 30% is building operation. If you drill into that one, almost 40% is heating, ventilation, and air conditioning. So more than 10% globally is related to stuff that Carrier do. So it's a pretty good place if you want to make some impact. I will touch upon domestic hot water as well, so maybe there is even more. But very large numbers worldwide is spent on buildings. So what's the vision? What do we want to do? Well, we would like to streamline how we design and commission and operate and monitor integrated energy systems. So one variant of, say, a V model, but formulated in a different way, start with customer requirements. What are the loads? What are the weathers that we need to deal with? And they may be changing. Architecture and technology selections. These are the very large, big, expensive decisions. Are we going to invest in solar or geothermal or nuclear or something else? High impact decisions. Then we need to drill down. We size the equipment and we select what units we will have and how many to get the efficiency, at least on paper. And then comes the controls challenge. Can we actually extract the efficiency that the plant was designed to deliver? Commissioning, can we actually make it run in a reliable way? And then there is operation and monitoring and all of that. There was a great talk by Michael Vetter and his co-workers yesterday on building control systems. And they spoke to how this process is often fractured because there are several handoffs through this process. And that means that it takes time, and many of the steps are highly reliant on experts. And we need to be in a very different place entirely. So the KPIs that matters is cycle times. So has to be days, weeks to design, commission, control these systems, not months and years, as is the current practice. There are a number of smart people who do this, and I'm sure you can all make this work, but there aren't enough of those experts. So we need to have tools and methodologies that educated engineers can use, not only the top experts. And then there is scalability. So how do we make this highly repeatable and less of one-offs? You know, there are very highly efficient buildings in the world. Maybe this is one of them, but they've proven to be quite difficult to repeat at scale. So this is the vision, and here are some challenges. And these are challenges that we are faced by our leadership almost every day, like how will this scale? So, key points of the talk. Modelica and FMI bring significant value to Carrier, and we use it across the life cycle. I won't talk about everything we do with Modelica, but I will give a brief account of it. So I want to say thank you for the good work that you're all doing to support our product development, and we have been using Modelica for 25 years. Then off to design, control, operation of integrated energy systems. Heterogeneity, scale, interconnections, and labs doesn't really exist in this world. You have to do it for real. They exist, like I said. There are many efficient buildings. Often they are one-offs, takes months to years, and require highly skilled experts. And from there, it's downhill, they degrade. So how do we change this to something that is much faster, leaner, and easier to work with? Systems engineering, we think, is one piece of the puzzle. So something we've all seen. I will touch briefly on it because I think it's an important enabler for what we need to do in our industry. And then, of course, if we can't lab our way through control tuning, as we may do with some of our equipment, modeling, optimization, simulation is the key enabler. There is no other way. So I will show what that could look like. So, off to integrated energy system. What are they? People define this. This is one definition. So, physical digital integration. Of course, there is a physical word, there is a digital word. Different energy sources, a very diverse environment, and energy storage. So, energy storage changed the game for us in many ways because it decouples the consumption and the production temporarily. So it gives a whole range of opportunities and a whole range of new challenges to tackle. We want efficient, affordable, reliable energy generation and delivery technologies. And to make all this work together, some of the strong teams, of course, integration, keyword for systems, optimization, could be designs, energy flows, thermodynamic efficiency, flexibility. A building is often repurposed, so may a city be. So need to have resilience and flexibility. And then there are sustainability goals and regulations. The benefits are clear: environmental, technical, economic, social, community. So there are many good reasons to work with integrated energy systems. So this is the picture from the European Commission, who thinks quite a bit about this. So the traditional way of organizing energy systems is rather siloed. So there is a silo for fuels, one for coal, one for gas, and one for electricity. Of course, there is some flexibility within each silo, but the way to build integrated energy system is to integrate it all. So everyone can talk to everyone. So we have microgrids, and we have integrated cities, data centers provide district heating, cooling. So it becomes a much more involved network with all the challenges that may entail. Zooming in a bit on the slice which Carrier is working with. So we work plenty with home energy management systems. So we equip our heat pumps with batteries, and we do grid interactions, and we try to aggregate the power need from very many residential homes and interact with the grid operator to relieve the grid. Demand response kind of things. We work on district heating and cooling systems, especially in Europe. And then we are quite focused on data centers. So much of my personal time is spent on data centers. Our permission to play, so to say, is that we have been doing equipment for very many years. Chillers and heat pumps, so that's sort of our entry point into this world. So very often for us, we come with equipment and we build our way into the systems opportunities. So this is an example of a very energy efficient building. It's a good example. One of my colleagues in Montreal, Michel Gravon, did this more than 10 years ago, La Défense, France. Smart building took fairly long time, took some fairly specialized hardware, took some very advanced modeling and simulation, and took a very talented team of engineers. They reached very good results, so 75% reduction of energy consumption. It's one of those examples which we are very proud of and which we have failed to reproduce. So this is not to say that this cannot be done by any stretch. Again, the challenge is to do it fast, with application engineers, and in a repeatable manner. That's the game. So why is it hard? Well, there's very diverse requirements. The number of equipment units is very large, like tens or 100 equipment units to orchestrate. The time scales are very diverse, seconds to minutes to hours to days, and if we talk about seasonality, years. And that can have some implications if you're in numerical analysis, maybe. The length scales are quite diverse, meters to tens, hundreds, kilometers. Very different technologies, some traditional chillers, gas boilers, heat pumps, and some new emerging technologies that we have at our disposal. Physics matter still, even in the era of AI, we believe physics matter quite a bit. There is policy, there is regulation to adhere to. So all of this needs to be taken into account. So it's a very diverse set of things you have to deal with. And if I distill this, I think there's really 4 things that are important that we aspire towards. You need really good domain knowledge. You need to understand how thermal systems work. You need some process. I think systems engineering is a reasonable way to do things, may not be the only one. We need to be able to predict physical behavior. So physical models, well-calibrated models are critical. And then there is optimization, simulation, modeling, all the stuff that we have been doing in this community for, 30 years. So these are the key elements of the solution. So I promised you to talk briefly about what Carrier has been doing in the Modelica space. So some of you have seen this. One of my colleagues, Klaus, helped me a bit because he's been around for a longer time than I. The first initiative was 25 years ago, fuel cells. UTRC, United Technologies, worked on this. I think some people in the room were involved in this. Very control-centric, so dynamics, simulation, and development of controls. There was also an effort on building systems. This was a few years later, also very focused on dynamics, focused on the controls development. So early on, this was the main thing. And then aerospace, there was an effort within United Technologies to develop air management systems. There are some customer testimonials on the web where you can listen to how this played out. And here we started, I was actually part of this effort. Here we started to work on things that went beyond dynamics. We did steady state, we did robust design, and we did a bit of optimization. There was also the equipment design where FMI, Simulink integration, Modelica modeling was a key enabler to speed up our control systems development. Still do that. We've done steady state with Modelica. So again, fairly focused on refrigerant cycles, but it also went to optimization. It also went to robust design. And now data centers is probably the major effort that I'm involved in. And you will find it all. It's dynamics, it's steady state, it's optimization, it's robust design. We try to do verification. So we also see what Claes Jacobsson projected is in his 2014 keynote. He said Modelica has to be more than transient simulation. And I've seen in our applications and also through this conference, we've seen there are many other applications of Modelica. So thank you for helping us doing all of this. So some have talked about systems engineering through this conference, so I will be rather brief in this. So systems engineering is how we get to an integrated product view and how we manage what will be delivered in terms of its components, communication, and the controls to coordinate into a systems that meet requirements. The V model has been, I think, dominant in many years. I think there is more refined views now, that successive refinements where requirements meet design candidates, and then we move to a down-selected design, and then we refine. And there is also the ideas by Alberto St. Giovanni Vincentelli on platform-based design, where there is a very explicit methodology to start at a high level of abstraction. You have requirements, and you hide everything below, and then you do design space exploration in a formal way to get to the design at that layer, and then you proceed. So the blue dot here is where I think many of us would sit. That's where you need models, that's where you need analysis as decision support to decide what the design will I proceed with. It's rather dry and it's rather abstract. So I asked Michael Vetter and Matthias Hülser if I could reuse one of their pictures from a paper they wrote on the topic. And I think this is a very good framing of how this could play out in the building domain. So highest level here could be city. Like, how do you plan out the energy system for a full city? Like very large decisions, and society has to be there, politics maybe has to be there, regulations has to be there. And then you drill down to districts, neighborhoods, and how do you distribute heat and water of different temperatures. And then you get to a building, like a data center may sit in the middle of some industrial area, provide heat, but also inside the data center, we need to design a cooling system that fits both with the requirements for the data center and which fits with the surrounding society. And then we are down to the equipment level, where we as Carrier feel quite comfortable. And now we're trying to push to be part of at least the building scale and maybe even the district scale. And we have some ideas and we have some business in that area. So let's talk about models through the V model. It's really a fairly heterogeneous range of models that we see that we need if we go through the cycle. So there is the requirements model, architecture formalization, behavioral model. We would like to do more of that in SysML, and we heard Eric Thomas gave a great speech yesterday on how they use SysML and integrate with Modelica, very inspiring to me. We are not that advanced yet. There is the physical modeling where Modelica is a great play, of course. Control systems, we have our building control systems. There is Simulink, there is sampled things in Modelica, so you can do controls there. So different options there. And then there is the optimization modeling, which is where I spend most of my time these days. Often very different types of models. Even you can use Modelica, but there is also other formulations. So modeling for X is a term we use to signify that whatever question you want to answer, that may lead you to different types of models. There isn't one model for all. And different tools, languages, SysML, Modelica, FMI, Python, Paniomo. I should probably add Casadi, yeah, Johan is there on this chart as well. Mixed integer, nonlinear program. So it's a very heterogeneous world. And if you peek into the mathematics, this is an optimization slide. You could formulate the simulation equivalent, of course. But the constraints, sometimes we can deal with linear. Nonlinear is probably our most prominent domain, and then differential equations, and maybe even to the level of partial differential equations. So this is sort of known territory. Decision variables in many cases, but not always. We have continuous variables which we optimize or simulate, but frankly, more and more we see discrete variables as part of the puzzle. So equipment units need to turn on and off, and we have discontinuous behavior sometimes that we need to deal with. So the discrete nature in combination with nonlinear dynamics, that's a very common combination that we need to optimize. And we found that to be rather hard. So off to a case study to show what this actually looked like. So the first case study is contributed by one of my colleagues at Fissmann, Bernd Hafner. They had a student challenge a couple of years ago. And this one sits, I would position it in the concept design phase. And we're going to focus on the optimization modeling that we did for this case. So we're in the world of mixed integer nonlinear programming. We choose to simplify a bit, and we went to linear mixed integer programming through some approximations. So let me introduce Greenville. So Greenville is it's a made-up city, but it's representative. So we have 9 different residential homes. There is a kindergarten. There is a field for solar, and there is a supermarket. And the city of Greenville, or maybe the village of Greenville, would like to design a new energy supply system. And they want heating in the winter, they want cooling, and they want a stable electricity supply. And they know about energy prices, and they also know about carbon emission. What's the carbon footprint for the different energy sources that they have at their disposal that they could select from. They have a handle on their requirement. They know roughly how much heating the village need every month. Maybe they know at every hour how much they need. They know how much cooling they need every month, and they know roughly how much electricity they need. So these are requirements, or one set of the requirements. And they realized that there is a vast number of combinations of architectures and equipment units and technologies that they could choose from. So they could go for thermal storage, there's ice storage, they could have batteries, they could burn oil if they wanted to, there is gas, there is solar, there is biomass, they could install geothermal, maybe there is a lake nearby that makes that appealing, air, and then they could buy electricity. So there's all these technologies, and then they have these requirements. And there are different people may have different views, of course. There may those who are very interested in the financials, so they will put a big weight on the financials. There are those who are very keen to show that Greenville will actually be the greenest village in Germany, so they weight CO2 very highly. And then there is the resilience, like we want to have a very solid and stable supply of energy. So there may be different interests among stakeholders. And to give some colors, there is very many different options for how you select equipment. So this is just a subset of what Fissmann has, and if we add carriers, equipment units, there are way more. And they all have characteristics. So they all have different characteristics in terms of first cost, and then they have different efficiencies. And efficiencies are never fixed, right? So efficiencies is always a function of operating conditions like water temperature or air temperature. So they may have very different operating characteristics, but it doesn't help really to look at the data sheet, because you need to match the characteristics of the equipment unit with your specific requirements, like how will this equipment unit operate in my world? Yeah, and here is more voices, like there are many voices who want to be heard in the design of this system. So I will fast forward. We did mixed integer discrete optimization. We did superstructure optimization. So we encoded the equipment unit characteristics. We encoded requirements, and then we come up with a couple of solutions. And this is quite significant. So if there's one point maybe around optimization that we should keep in mind, it's never about one point. It's never about finding the optimal solution. It's always about finding the trade-off between the KPIs that we care about. And then you can have a rational discussion about decision making, like what do we select? So here we see a typical Pareto curve. So on the y-axis, we have CO2 emissions. On the x-axis, we have annualized cost, so it's both the first cost and the operating cost. And it's typical, it's more expensive to be very carbon neutral, maybe even, and it's more expensive to less expensive to be less CO2 friendly. And now we can talk about what are the pros and cons for these different solutions. And we can also look at the mix. So if you look to the right, you see as the lowest cost solution, we can install less capacity in the energy converters like PV and stuff, because here we have boilers which are not very environmentally friendly maybe, but they fire up very quickly and we can run them in any condition. So in sort of corner cases of the requirements, we can use that kind of equipment to quickly fire them up, and then we can have less of other energy converters. Whereas if we want to get rid of gas boilers, well, then we have to invest in more capacity, like more PV and maybe even storage. And now you can start to think about, do we have all the space we need for the PV? Is that how we're going to use our land, or do we pick something in between? And then if we try to illustrate this, I picked two. So the solution that is the cheapest, but with the largest CO2 footprint. Here we have a gas boiler. In the middle, we have a solar collector. We have some PV, but the gas boiler will carry quite a bit of the load. To the right is a much more lower CO2. However, it's a more expensive solution. So here we invested in storage. So we invested in an ice storage to be able to carry the cooling load in the summer, so we don't have to run the air conditioning units so hard. So here you see an example of the trade-offs. And if you think about how many architectural options are there to connect all these different units, and you think about how many units are there, it's a vast number of combinations. Like it's more combinations than grains of sand in the universe. It's impossible to enumerate. So you have to have analytic methods, you have to have models, you have to have optimization methods. And by the way, this applies to chiller plants and other things as well. So it's a nice story, but we had challenges. So what do we struggle with? Well, we definitely struggle with the scale of the optimization problems. We get very large systems if we want good accuracy. Now we have this nice architecture. Now we struggle, how do we carry this on to control and dynamics? Like how do we control these things? So now we have the models sits in Python with Pyomo. They're great for mixed integer. Now we also need Modelica models, and how do we make that transition in a safe way, and parameter consistency, etc. Impact of uncertainty and system robustness. We heard a bit about that in the keynote, and there are others who are talking about that. That's a challenge. And then there is the tooling, very many platforms. There are help. FMI helps a lot to integrate these things. Python and those environments helps us quite a bit, but we still have the tooling integration challenge. And then there is accessibility. It's a very clever person who set this up and run it, and we need to be enabling others to do this as well. Again, our 3 KPIs. So this is one example. In one hand, it's an interesting problem. It's intellectually challenging. We have some emerging solutions, but we also have some challenges. So the second case study I will talk about is about data centers. Now we are at the field operation stage. So this data center is already running, and our job is to maximize the efficiency of the data center. So energy efficiency is important for data centers. Uptime is more important. SLA, service level agreement adherence, is more important, but energy is one of the important places. And here we used Modelica, and we also used some optimization methods. So we kind of framed where we sit in the V-cycle, and we framed what technologies we used. So this is a typical data center inspired by reality. It's not huge, 20 megawatt of IT power. We hear now about data centers, 100 megawatt hour, maybe even gigawatt hour data centers. 20, I should say, megawatts, not megawatt hours. 12 chillers on the roof. There are 96 air handling units and 4 IT spaces. So it's non-trivial, at least to us, it's non-trivial. Again, it's also not the largest one we see. And there is some impressive pumping and piping in these data centers. Very large flows of water. Just the thermal inertia of the water pipe is quite impressive. So if we abstract this a bit, there are 3 key pieces of a data center. So there is the IT space where the load is reacted to the air, so heat is reacted. Then there are air handlers, could be these days cooling distribution units for liquid cooling as well. And then there are some type of cooling equipment, chillers, water-cooled, air-cooled. In this case, it's air-cooled. So the heat is transported through this chain out of the data center. So server racks to the air handlers that shifts the heat into the cold circulating water, and then it's reacted by the chillers. And then the control objective that we selected here is to minimize the energy consumption of the integrated system. It's very easy to minimize the energy of the chillers, but that may not mean that the data center as a whole consumes less energy. So it needs to be system-wide optimization. And here we selected to look at how many equipment units should be running, because for a given load, like 50%, you can have 3, 4, 5, 6, 7 chillers running. But the question is, what's the optimal number? And that comes down to efficiency of each of the chillers. So each chiller has an efficiency curve, like as a function of air, as a function of the water temperatures, as a function of the water flow rates, you have a given efficiency. The efficiency curves doesn't look like that. That's proprietary information that we won't share. But you can think about this as a curve in a high-dimensional space where you want to find the peak efficiency point, not only for the chiller, but for the system as a whole. So again, we want to decide how many chillers are we going to run. And we defined a few cases, so constant load, 25, 50, 75, 90%. Some data center very often run at part load conditions. That's good news, right? Because then we have more degrees of freedom to optimize. And we had some varying load to see how the system reacts to varying loads. And then we picked 8 locations. Our sales team thought these were particularly important to study. So we pulled weather data, relative humidity and temperature off the web. And again, we turned the crank. We did, in this case, our methodology was unit commitment. So we solved a discrete unit commitment problem. We got all our chiller curves, all the pump curves in the models. And then we looked at what do the solutions look like and how much can we save. And we can save quite a bit, at least for this case. So we compared the baseline installed control system. Maybe we start to the right. So the blue curve is the baseline controls. And the baseline control system runs fairly few chillers for a given load. And it doesn't stage up and stage down very much. It runs like roughly three chillers. That's a good number for these load conditions. And the optimal solution shows that for these particular chillers, it's much more advantageous to run more chillers, because these chillers, they have a free cooling option. So they're very efficient when they run at low capacity. So more chillers, each chillers carry a lower load, and then we get to higher efficiency. And for part load conditions, the analysis here show we can save a ton of energy. For higher load conditions to the right, single digit. Take it with a grain of salt. It's not unrealistic. It's possible to save energy in data centers. However, the specific numbers here may be biased by some of the selections we made. So we showed this to our leadership, and we were proud, of course. We thought this was a great result, and he looked at us and he said, "Oh, really? I'm surprised you can't save more." Okay. But he said, this is not the question. I don't doubt that, like Johan, smart people like you and your PhDs in your team, you should be able to do this. That's what we expect from you. The question is if you can devise a solution where you enable the larger sales teams and commissioning teams within Carrier to do this within weeks. And we need to do it not for one data center every year, because I think that's what you can do, maybe 2 if you're good. But we need to do it for tens and hundreds of data centers every year. So the challenge that I positioned first comes straight from our leadership. It's a business challenge. Like, how do we make this scale? So we also did Modelica, of course, because the optimization we did was steady state or quasi-steady state, and the world is never in steady state. So we had to answer questions around how robust would these solutions be if we actually apply them to running data centers. So we used the buildings library from Lawrence Berkeley, like many others, some at this conference. So we modeled the chiller plant, we modeled the IT spaces, we modeled the air handling units, all 12 chillers, simplified models, of course. We also modeled the building management control system. And this is very important because any building has a running control system that makes sure that set points are tracked and that disturbances are rejected. And we're never going to remove that, of course. So we add an optimization layer on top of the BMS system. And that means we also need to model the BMS system, because otherwise we don't know how the system will actually react. So this is also part of what we've done. And again, it links very closely to some of the presentations on the control description language and the ASHRAE standards that some of us listened to yesterday. So having done this, we can run annual simulations. So full up, we run a year. It's not super quick, but it's not super slow, an hour or 2 maybe. We can look at air temperatures in the IT hall, which is critical, of course, because when we start staging equipment up and down, the water conditions, they change ever so slightly, and that can impact the room temperature. So we can actually quantify with some fidelity the power consumption, and we can also quantify how the air temperature fluctuates. So again, it's a good project to work on. We have good results, we think. We also have challenges. So one challenge comes up here again. We have 2 different model frameworks, like mixed integer optimization, which we think is the appropriate methodology to solve the staging problem. And then we have Modelica models, and ideally we would like them to be fluently consistent without manual work. Now we do it sort of manually. We saw similar challenges in some of the sessions yesterday, like the AI methods, like how do you bring Modelica out of Modelica and then maybe back in. So we struggled with that. We worked hard to get scalable simulations. The tools that we use are very good, scalable, robust Modelica tools, best of breed. Even so, the scale of the problems are still challenging. And then component uncertainty, how does that propagate to systems? Different tooling, different platforms, and then how can many people use this? So to wrap this up, we need to do it fast. We need to lower the bar for less experienced engineers to do this design, commissioning, operation. And we need to have something that is repeatable. Scalability, tooling, consistency, and uncertainty are some of the challenges. So there are other things that I could talk about and I'm interested in talking about. I haven't heard OFMI yet. I'm waiting for that. Maybe, Dirk, it's on your wish list. Come talk. I'm here all day. Okay, thank you.
Thank you very, very much. We want to also show our appreciation. Please,
thank you very
let's thank
much.
our speaker once more.
Thank you. Thank you very much.